Hello everyone! Today, we begin to learn about the mutual independence of events. First, let's look at the learning objectives. Firstly, by exploring practical problems, discover and understand the concept of world independence. Secondly, the ability to apply the probability of independent events occurring simultaneously to solve some simple practical problems. Thirdly, experience the process of analogical induction through practical problems, appreciate that mathematics originates from life and serves life, and enhance the awareness of applying mathematical knowledge to solve problems. Now let's review. First, let's take a look at problem 1. What is conditional probability? Generally, we set A, B as two events, and if the probability of event A is greater than 0, the probability of event B occurring under the condition that occurs is equal to the probability of event AB divided by the probability of event A, which is the conditional probability of B occurring under the condition that event A occurs. This equation can also have variations where we can write that the probability of event AB is equal to the probability of event A multiplied by the probability of B occurring under the condition that occurs. Okay, let's continue reviewing. Please refer to question 2. 3 lottery tickets, one of which can win. Now, 3 students are drawing without putting them back in order. Will the winning probability of the last student who goes to draw be affected by whether the first student wins? It will affect, for example, if event A is set as the first student who did not win. Let event B be the last student to win the prize. So based on the conditional probability, we can conclude that under the condition of event A occurring, the probability of event B occurring is equal to 1/2. Therefore, the occurrence of event A will affect the probability of event B occurring. Okay, now let's look at question 3. Question 3 is very similar to question 2, just one word apart. One of the 3 lottery tickets can be won, and now 3 students will draw them one by one. May I ask if the winning probability of the last student who goes to draw will be affected by whether the first student wins or not? It won't be affected. For example, event A is when the first student did not win, and event B is when the last student won. Because the student in incident A had to return the lottery ticket after drawing it, his behavior did not affect the outcome of incident B. So the occurrence of event A will not affect the probability of event B occurring. Just now we discussed the issue of 3 lottery tickets being returned or not returned. Now let's switch to a different type of issue. Please refer to question 4. Throw 2 evenly distributed coins one after another. Does the result of the first coin toss affect the result of the second coin toss? Please think about it. There should be no impact. For example, if the result of the first coin toss is positive and upward, it is event A. If the result of the second coin toss is negative and upward, it is event B. These 2 events are from 2 random experiments conducted under the same conditions, so the occurrence of event A will not affect the occurrence of event B, and vice versa. We can call event A and event B independent of each other. Let's take a look back at problem 3, which is the issue of 3 lottery tickets being returned for extraction. In this question, the occurrence of event A does not affect the probability of event B occurring. We can say that in the experiment with replacement, the results of the 2 extractions are also independent of each other. We can express it using an equation, which means that under the condition of A occurring, the probability of B occurring is equal to the probability of B event occurring. According to the definition of conditional probability, the probability of event AB is equal to the probability of event A multiplied by the probability of B occurring under the condition that occurs. In this way, we can further obtain that PAB is equal to PA multiplied by PB. This is a very important conclusion that we can use to determine whether 2 events are independent of each other. Now let's start learning about the independent concepts of new knowledge. Let AB be 2 events. If the probability of event AB occurring is equal to the probability of event A occurring multiplied by the probability of event B occurring, we call event A and event B independent of each other. When you see independent concepts, you may feel that they are somewhat similar to mutually exclusive events. We must accurately and carefully distinguish between mutually independent events and mutually exclusive events. Firstly, a mutually exclusive event is 2 events that cannot occur simultaneously. It has the law of addition, where the probability of the sum of A and B events is equal to the probability of an event occurring plus the probability of B event occurring. And independent events, the occurrence of these 2 events does not affect each other, they can occur simultaneously. It has a multiplication formula. The probability of a B event occurring is equal to the probability of an event occurring multiplied by the probability of B event occurring. Okay, Now let's take a look at an exercise. Roll a dice. Event A is the occurrence of 1 point, and event B is the occurrence of 2 points. Are events A and B independent of each other? Please think about it. This question is different from the one where 2 coins were tossed one after another earlier. We throw a dice, and once one appears, it is impossible to have 2. Conversely, if 2 dots appear, it is also impossible to have 1. So events A and B are not independent events, they are mutually exclusive events. Next, we will continue to learn the probability formula for independent events occurring simultaneously. If AB are independent events, then the probability of AB occurring simultaneously is equal to the probability of an event occurring multiplied by the probability of B event occurring. That is to say, the probability of 2 independent events occurring simultaneously is equal to the product of the probabilities of each event occurring. As we mentioned earlier, this formula is very important. It not only helps us identify whether 2 events are independent of each other, but also allows us to calculate the probability of independent events occurring simultaneously. When applying this formula, special attention must be paid to meeting 2 prerequisites first. Firstly, the 2 events must be independent of each other, and secondly, they must occur simultaneously. We can generalize the probability formula for independent events occurring simultaneously. If events A1, A2, and N are independent of each other, then the probability of these N events occurring simultaneously, that is, P1, A2 until N, it is equal to P1 multiplied by P2 multiplied until Pn. Okay, let's continue learning. Please refer to question 5. A deck of playing cards, we remove the big and small kings, and take any card from this deck. Let event A draw king, event B draw red card, and event C draw jack. So are each of the following pairs of events independent of each other? The first question is to discuss whether event A and event B are independent events. Event A is to draw king. Event B resulted in a red card. If a red card is drawn, it is possible to draw either the peach king or the cube king. That is, it is possible to draw the king, so events A, B may occur simultaneously. We will further calculate. We look at the probability of event A occurring, according to the formula of classical probability. There are a total of 52 cards, and we have them as the denominator. Therefore, there are 4 king cards, and we have them as the numerator. The probability of drawing king is equal to 1/13. We will then calculate the probability of event B occurring, which is the probability of receiving a red card. Half of the 52 cards, or 26 cards, are red cards, so the probability of event B occurring is 1/2. The significance of event AB is to draw both the king and the red card, that is, to draw either the peach king or the cube king. We will still apply the calculation formula of classical models, and the denominator is still 52 cards. Therefore, the numerator can only be 2, which is the combination of the red peach k and the square k, which is equal to 1/26. From this, we can conclude that the probability of AB events occurring simultaneously is equal to the probability of events occurring multiplied by the probability of B events occurring. This conforms to the concept of mutual independence. Therefore, event A and event B are mutually independent events. Let's summarize the methods for determining whether 2 events are independent of each other. The first method, also known as the direct method, is to make a direct judgment based on practical significance, such as whether there is a problem of putting it back or not. The second method is the definition method. If event AB satisfies that the probability of AB events occurring simultaneously is equal to the probability of events occurring multiplied by the probability of B events occurring, then event AB is an independent event. The third method is the conditional probability method. When the probability of event A occurring is greater than 0, we can use the condition that the probability of event B occurring under event A is equal to the probability of event B. We still use the first 2 methods more frequently. We just did the first question of question 5, now let's do the second question to discuss whether event A and event C are independent of each other. Event A is to draw king. Event C is to draw jack. If you draw king, you cannot draw jack, and vice versa, if you draw jack, you cannot draw king. Therefore, A and C are mutually exclusive, and events C and A cannot occur simultaneously. Therefore, the probability of AC occurring simultaneously is equal to 0. Through the calculation of the first question, we also know that the probability of an event occurring is not equal to 0, and the probability of C event occurring is also not equal to 0. Therefore, the probability of AC events occurring simultaneously is not equal to the probability of an event multiplied by the probability of C event, which does not conform to the concept of mutual independence. Therefore, A and C are not mutually independent events. Through question 5, everyone should already be able to distinguish whether two events are independent of each other. Next, let's further study. Please refer to question 6. Shooting athletes A and B each shoot at the target once, with a probability of 0.8 for athlete A and 0.9 for athlete B. Ask the first question about the probability of both people hitting the target, and ask the second question about the probability of at most one of the two people hitting the target. Let's first set it to shoot once and hit the target as event A. We have already shot once and hit the target as event B. Then we will solve the first problem. The probability of both people hitting the target, which is the probability of event AB occurring simultaneously. At this moment, we certainly want to use the probability formula for independent events occurring simultaneously. The problem is, we need to first determine whether event A and event B are independent of each other. Event A, if it occurs, is the target hit by a single shot from A. Will it affect the occurrence of event B? In a purely mathematical sense, it is clearly not affected. So we can say that AB is two independent events. In this way, we can apply the probability formula of independent events occurring simultaneously to solve the problem. Firstly, let's assume that both people hit the target, event C. Then PC is also PAB. The probability of AB events occurring simultaneously is equal to the probability of events occurring multiplied by the probability of B events occurring. According to known conditions, the probability of being hit by armor is 0.8. The probability of hitting B is 0.9. Therefore, the final conclusion is 0.72. Okay, now let's take a look at the second question. The probability that at most one of the two people hits the target. When encountering at most this type of problem, we can think of its opposite. What does it mean to have at most one person hit the target? That is to say, as long as two people hit the target at different times. Therefore, we assume that at most one of the two people hits the arrow as D. The probability of event D occurring is equal to 1 minus, and the probability of event AB occurring simultaneously is equal to 1 minus 0.72 equals 0.28. Can you summarize the general steps for calculating the probability of independent events occurring simultaneously through the study of question 6? Firstly, determine whether each event is independent of each other. Secondly, ensure that these events can occur simultaneously. Thirdly, calculate the probability of each event and then integrate them using the probability formula for independent events occurring simultaneously. Now let's do an exercise. There are 3 light bulbs connected in parallel on a chandelier. If the probability of each light bulb not illuminating properly during a certain period of time is 0.1, 0.2, 0.1, then what is the probability of the chandelier being able to illuminate during this period? If the chandelier can provide normal lighting, as long as not all 3 light bulbs are broken at the same time. So let's assume that the chandelier can illuminate during this period as event A. The probability of event occurring is equal to 1 minus 3 light bulbs, and the probability of not being able to illuminate properly. That is, subtracting 0.1 from 1 multiplied by 0.2 multiplied by 0.1, and finally equals 0.998. The probability of the chandelier being able to illuminate during this period is 0.998. Next, we will review and summarize this lesson. We first learned the concept of mutually independent events and their judgment methods. Then, we learned the probability formula for independent events occurring simultaneously. The final step is to calculate the probability of independent events occurring simultaneously. Okay, that's all for today's learning. Goodbye, everyone.